During this fourth lesson, what we are going to see is how to get to a mathematical representation that allows us to define any wave motion that we want to analyze and that is occurring in our environment. For this, first, what I am going to do is to observe and analyze the different graphical representations that we can make to have an idea of that wave motion. From the analysis of its graph, we are going to get to a mathematical representation, and for this we are even going to introduce new physical magnitudes such as the angular frequency, pulsation, and the number of waves associated with the wave motion. If we observe at the beginning wave motions around us, such as the perturbation in the waves of A, the perturbation produced on the surface of a fluid with cylindrical wave fronts, as in this case, or linear wave fronts, as in this case, we see that a graphical representation could occur through a sinusoidal function, as what we can observe simply by this image. It turns out that if we observe other types of waves, such as stationary waves, we see that those stationary waves, I can also represent them as traveling waves to the right that are superposed with traveling waves to the left, and they give us this stationary pattern where the maximums and minimums occur at the same point of the space. We have here a superposition of waves, and that same superposition of waves is going to occur if we try to represent graphically, for example, the sound A sharp produced by this clarinet. The pressure wave that represents the sound of that wave produced by the clarinet would be this graphical representation here. Clearly, I cannot make this graphical representation simply by a pure harmonic wave, a sine or a cosine. No. I will need to superimpose different harmonic waves to get to this sound, to this representation of the sound. Very well. What I am going to tell then is with the application of what I am going to call from now on the principle of superposition of the waves. When I try to analyze a perturbation that is occurring in the middle, it turns out that I am going to take into account that this perturbation is propagating in the space, but also for the same point of the space that perturbation is varying. There is a double dependence in terms of vibration, in terms of perturbation. On the one hand, the spatial dependence, and on the other hand, the temporal dependence. Well, if I look at this, as we have seen a little bit here, in a reference system that is fixed absolute and a reference system that moves with my propagation, I can make a first mathematical representation saying that the perturbation that is propagating is a function of a point of the space prime x. Now, that perturbation is propagating with a certain speed, the propagation speed, and the space that is moving is determined by that speed and the time that has taken from the point that has occurred. If I want to relate the different spatial points in the moment in which I am now represented by the nomenclature of prime x and prime y, or the origin represented by the reference system absolute x and y, it turns out that I see that the deformation in terms of the variable of the ordered prime e is equal to y, while I can relate its position with respect to an initial position x equal to 0 in the reference space absolute. We are going to call it blue from this expression. I know that the current position is defined. This point here has a value x that corresponds to the previous one if I subtract the space that I have traveled. Prime x would coincide with the position of x minus the space that has traveled my perturbation, with which I come to a mathematical expression that tells me that the deformation in the middle, in the absolute space, is defined in any moment if I take into account the spatial variable and the temporal variable. This is what is going to define from now on the equation of a wave. In general, it is formed by a single frequency, by a pure harmonic movement, a sine or a cosine or a superposition of waves. This wave equation, also called wave function in many biographies, we will always find it. If, in particular, I look at a harmonic wave defined by a single frequency, it turns out that if I make the same representation, in this case in the space, considering the x space as the axis of abscissa, I know that 2 points that are the closest possible in the same state of vibration are represented by the wavelength. What would be the mathematical representation of this function here? We all know it. It would be a representation given by the sine function. It would be a sinusoidal modulation, and the phase, the argument of that function in the x space, prime x in this case, would be given here. In the absolute space, here would be the representation prime x. We have seen how to represent it and how to relate it with points of the previous space. Very well then, if I work with a wave and I see its evolution taking as axis of abscissas, or seeing the evolution in the space or the evolution in time, it turns out that both descriptions are given by the wave function that has the double spatial xy temporal dependence from time. We see that the relation that I get then is that the perturbation that is produced, and here we have to take into account that it gives account of the perturbation, and it can have dimensions of a pressure wave, of a wave that represents the electrical field, the magnetic field, of the elongation of the deformation, or the height that the droplets of water suffer on the surface of a liquid, of the deformation of a well, and therefore it would also be, in this case, units of its dimension would be of length. I will have the same dimensions as the function I, and in the argument we have that dependence where also appears the propagation speed, and that we have already seen that it is related to the wavelength and with the period of my oscillation. I can pass the value of 2pi that would represent the phase of my mathematical representation inside, and I get then a new definition of the magnitudes that would be, in this case, the angular frequency or pulsation that is given by 2pi divided by the period and the number of waves from 2pi by the wavelength. Notice that then the pulsation and the number of waves will allow me to determine the periodicity in time and in space. And I have different representations or ways of rewriting, in this case for a pure harmonic function defined by a sine function, different mathematical representations as I have seen here. This would be perhaps the shortest, and from it breaking the physical magnitudes that we are introducing versus dependence, that in terms of a pure function. But we do not always have some undulating movements that we can represent by pure functions. Here, for example, in this cardiogram, that would represent then the evolution of the menstrual valve of the heart of a dog. In this case, we see how this variation of what is being produced, the palpitation in the heart, is given by this movement. Look, it comes here very well described in this real cardiogram. Also, what would be the pressure wave of the sound of A-sharp clarinet sustained by this representation? What would I have here? Well, I also have a graphical representation, but it would not be given by a pure sine function, but by a superposition of harmonic functions. We will see how to get to that representation. But we see here how I do have a periodicity, and I will be able to represent graphically, and a first approximation from harmonic functions, a mathematical representation of different undulating movements. We have different representations, therefore I have to distinguish between pure harmonic waves, a single frequency, or see how to compose them when I have several frequencies. And we have introduced two new physical magnitudes, the angular frequency and the wave number, taking into account the definition of 2pi divided by the wavelength. We are going to continue applying everything we are seeing and everything we have learned in these lessons in the next lesson.